Hello everyone, I am Dr. VRAO-PHYSICAL. In the last videos, we had gone through the concepts of chemical equilibrium chapter. Now we shall go through the some problems in chemical equilibrium chapter, right? So problem 1 is okay. So problem 1 is 0.96 grams of HI was heated to attain equilibrium. 2HI gives rise to H2 plus I2. The reaction mixture on titration requires 15.7 ml of n by 10 hypo solution. Then calculate the degree of dissociation, right? So they asked to calculate the degree of dissociation. So degree of dissociation. Okay. So from the earlier videos, we know the formula for degree of dissociation. That is, degree of dissociation alpha is equal to moles dissociated by initial moles right. So that is the formula to calculate the degree of dissociation. Moles dissociated by initial moles dissociated at equilibrium. Here the moles dissociated at equilibrium and these are the initial moles, right. So by calculating the moles dissociated and initial moles and we substituted in this fraction, we can get the degree of dissociation alpha, right. So first we need how can we calculate the moles dissociated and initial moles from the given data. The given data is there is a 0.96 grams of HI was heated. HI was heated to attain the equilibrium. Then what is that equilibrium? 2HI gives rise to H2 plus I2. This is the equilibrium that established by heating 0.96 grams of HI. How can we calculate the initial moles? They given that 0.96 grams of HI. They given that 0.96 grams of HI. So they gave that 0.96 grams of HI. So by dividing the 0.96 grams of HI with its molecular weight, we can get the initial moles, the number of moles of HI. So initial moles is equal to what is the weight of HI? 0.96. So what is the molecular weight of HI? This is 128. So 0.96 by 128 which comes out to be 0.0075. It comes out to be 0.0075. So we can write it as 7.5 into 10 power minus 3. We can write it as 7.5 into 10 power minus 3. These are the initial moles of HI, and at initial state the concentration of H2 and concentration of the moles of H2 and I2 are 0. But at equilibrium during the establishment of equilibrium, X moles of HI dissociated to form to establish the equilibrium with H2 and I2. That means X moles of HI dissociated to form the equilibrium with H2 and I2. So 7.5 into 10 power minus 3 in which X moles dissociated. During the establishment of equilibrium, X moles from initial moles dissociated are consumed to form how many moles? Moles of H2 and I2. So there is a technique for how many moles of H2 or I2 is formed. There is a simple technique for calculating the number of moles of H2 and I2. So you take the what is it called, stoichiometric equation. You should take the stoichiometric equation, that is 2, the stoichiometric coefficient of HI is 2 and H2 is 1 and I2 is 1. Okay, IT is 1. Okay, next this is the 2 stoichiometric coefficient of HI, and in which x moles dissociated. X moles dissociated. Then 1 mole of H2, how many moles of H2 formed? Then x cross multiplication, x by 2. So x by 2 moles of H2 is formed. And of course for I2 is also, it is also 2 moles, for 2 moles x moles is dissociated, then 1 mole, that is I2 is also x by 2 moles is formed. X by 2 moles are formed at equilibrium, that is on x moles, 7.5 into 10 power minus 3 is the initial number of moles. Out of that initial number of moles, x moles dissociated, and that x moles dissociated gives x by 2 moles of H2 and x by 2 moles of I2, right. So next what we should calculate, moles dissociated by initial moles. Okay, so but the given data is the reaction mixture on titration, that after the establishment of equilibrium, the reaction mixture on titration requires 15.7 ml of n by 10 hypo solution. Okay, you should remember one point, whenever is titration is going on, milli equivalents or millimoles of titrant is equal to milli equivalents or millimoles of analyte, millimoles of analyte. Okay, so that is whenever the titration is going on, milli equivalents. Why I am taking milli equivalents? Because the given data is volume in ml and the concentration is normality. That's why I take milli equivalents of I2, because milli equivalents, why I am taking milli equivalents of I2, hypo react with iodine. Okay, there is a reaction between I2 and hypo. Okay, so that's why milli equivalents of I2 is equal to milli equivalents of hypo, milli equivalents of hypo. So how can we calculate the milli equivalents of I2? That is weight by gram equivalent weight into 1000. That is the milli equivalents of I2. And the milli equivalents of hypo, they given that data, milli equivalents of hypo. How can we calculate the volume in ml into normal concentration in normality, that is 0.1, 0.1, that is 15.7 into 0.1, 0.1 means 1 by 10, that is 1.57, that is 1.57. So weight by gram equivalent weight of I2 is equal to 1.57 into 10 power minus 3. Okay, 10 power minus 3, we are taking 1000 to right side, right, 1.57 into 10 power minus 3. So moles of I2 formed at equilibrium. How can we calculate the moles of iodine formed at equilibrium? That can be that is okay, and moles of iodine, moles of I2 formed at equilibrium during the titration, formed at equilibrium, equilibrium is equal to its weight 1.57 into 10 power minus 3, 1.57 into 10 power minus 3 by 2. Why I am dividing with that value with 2? Because when the titration is going on, there is a reaction takes place between iodine and hypo. That reaction is I2 gives rise to I2 plus 2S2O3 2 minus gives rise to 2I minus plus S4O6 2 minus. So Iodine thiocyanate is converted into tetrathionate, and in this iodine from 0 oxidation state to -1 for 2 iodines 2 electrons, that way we are dividing with 2, right, we are dividing with 2, that is the practical value. But according to our hypothesis, our theoretical what is it called, according to equilibrium that we hypothesized, okay, that is moles of iodine formed at equilibrium, moles of I2 formed at equilibrium is x by 2. So these two are equal, then we can x by 2 is equal to 1.57 into 10 power minus 3 by 2. So 2 get cancelled, x equal to 1.57 into 10 power minus 3. Okay, 1.57 into 10 power minus 3. So what is x here? X is moles dissociated, x moles dissociated, and we know the moles dissociated, and we know the initial moles. What is the number of initial moles? 7.5 into 10 power minus 3. So degree of dissociation alpha is equal to moles dissociated 1.57 into 10 power minus 3 by initial moles is 7.5 into 10 power minus 3. 10 power minus 3, 10 power minus 3 get cancelled. Okay, so it is when we multiplying with 100 and 100, that is 157 by 750, 157 by 750, which comes out to be 157 by 750. This fraction comes out to be 0.209. This fraction comes out to be 0.209. So alpha is 0.209. To avoid the time wastage, I directly substituted the fraction value 157 by 750, that gives that comes out to be 0.209. Then we can calculate the percentage of degree of dissociation. Degree of dissociation, that is given by 0.209 by 100, 0.209 by 100, which comes out to be, you know that you can get the value from this value, that is 20.9. Degree of dissociation is 20.9. In this way we can calculate the degree of dissociation, because most of the problems they ask to calculate the degree of dissociation, right? Okay, problem 2 is at 273 Kelvin and at 1 atmosphere, a liter of N2O4 decomposes to NO2 as N2O4 gas is equilibrium with the 2NO2. To what extent has the decomposition proceeded when the original volume is 25% less than the existing volume? Here also they asked to calculate the to what extent has the decomposition proceeded. Decomposition or degree of dissociation, everything is one, all are same. So degree of dissociation or decomposition, degree of dissociation, we know the formula for a degree of dissociation, that is moles dissociated by initial moles, right, moles dissociated by initial moles, right. Okay, so they ask you to calculate the degree of dissociation, but when 273 Kelvin and at 273 Kelvin and at 1 atmosphere, a liter of N2O4 decomposes to NO2 and the equilibrium is N2O4 gas is in equilibrium with 2NO2. So in order to calculate the moles dissociated and initial moles, we have to write the equilibrium. So equilibrium at initial state, there is a liter of N2O4, that is initial moles or volume. Moles is directly proportional to volume. So A gives rise to initially these are 0. Okay, so at equilibrium, during the establishment of equilibrium, x moles of A decomposes to form something moles of NO2. Okay, so x moles, what is that? X moles x moles of N2O4 decomposes, and let us calculate the how many moles of NO2 is formed. Already I told one simple technique. Take the stoichiometric equation, that is N2O4 stoichiometric coefficient is 1 and NO2 stoichiometric coefficient is 2. So, for 1 mole x moles dissociated, for 1 mole x moles dissociated, for 2 moles how much? 2x. So, this is 2x. Okay. So, 2x moles of 2NO2 is formed. Okay, and moles at equilibrium, when we add these total number of moles, then we get the total moles at equilibrium. Total moles at equilibrium, total moles at equilibrium is equal to A minus x plus 2x, that is A plus x moles formed at equilibrium. Okay, and what they given that to what extent of dissociation has proceeded when the original volume is 25% less than the existing volume, original volume. So, we need to calculate the original volume, because original volume they given that original volume is 25% less than the existing volume. So, original volume is 25% less than the existing volume. So, 25 out of 100%, 25% is less, then what is the percentage remains? 75%. So, 75%, that is 75% means 75 by 100. Okay, they given that to what extent has the decomposition proceeded when the original volume is 25% less than the existing volume. So, then initial moles is equal to 75 by 100, because the existing volume is 75 by 100, and initial at moles at equilibrium, that is A plus x, because we should equate the initial moles is equal to 75 by 100 into moles formed at equilibrium. Total moles formed at equilibrium, moles at equilibrium. So, initial moles is A, and moles formed at equilibrium 75 by 100. Why we are taking 75 by 100? Because original volume is 25% less than the existing volume, and 75 by 100 into moles at equilibrium, moles formed at equilibrium is A plus x. Okay. So, 75 by 100, this is 325s and 425s, A plus x, and 4A gives is equal to 3A plus 3x. This is A is equal to 3x, and x equal to A by 3. X equal to A by 3. That is we get the moles dissociated. We get the moles dissociated because x is the moles dissociated from initial moles. So, we get the moles dissociated, x is equal to A by 3, and we know the initial moles is A moles. Okay. So, alpha is equal to moles dissociated, that is A by 3, and initial moles is A. So, A by 3A get cancelled, 1 by 3. 1 by 3 means that is 33.33%. 33.33%. 1 by 3 means the percentage is 33.33. So, degree of dissociation is 1 by 3, and percentage of dissociation is 33.33%. Okay, right. Okay. Problem 3 is the equilibrium constant Kp of the reaction NH4HS is gives rise to NH3 gas plus H2 gas at 20 atmospheric pressure will be. Okay, they asked to calculate the Kp value. They asked to calculate the Kp. So, let us write the equilibrium, that is NH4HS is gives rise to, that is it is a solid okay, NH3 gas plus H2 gas, right. So, initial moles we can take a number of moles of initial moles is 1 and initial these concentrations are 0, okay. And we can write the equilibrium constant. What they asked to calculate? They asked to calculate the Kp. So, Kp is equilibrium constant expressed in partial pressures. Equilibrium constant in Kp is equilibrium constant expressed in partial pressures. So, how can we write the equilibrium constant in partial pressures? Partial pressure of products. So, here the stoichiometric coefficient is 1. So, partial pressure of NH3 power 1, no need to write the 1, okay, and partial pressure of H2, okay, and we no need to write the partial pressure of NH4SS because it is a solid, so no need to write that. So, equilibrium constant is Kp is equal to partial pressure of NH3 and partial pressure of H2. So, by calculating the partial pressure of NH3 and partial pressure of H2 and after substituting in this equation we can get the Kp value. So, partial pressure of NH3, how can we get the partial pressure of NH3 is equal to mole fraction of NH3 into total pressure, that is total pressure. Already they gave that total pressure, that is 20 atmospheric pressure. We need to calculate the mole fraction. So, we need to calculate the mole fraction. How can we calculate the mole fraction? Mole fraction is moles of the substance by total moles, moles of the substance by total moles, right, moles of the substance by total moles, right. So, at equilibrium, for example, if we take x moles dissociated, x moles are dissociated, then how many moles of ammonia and H2 is formed? There is a simple technique to calculate the number of moles of H2 and NH3 formed at equilibrium. That is, take the stoichiometric coefficients of reactant 1 and NH3 is 1 and H2 is 1. Okay, for 1 mole we take x moles dissociated. So, for 1 mole of NH3, how many moles dissociated? X into 1 by 1, that is x. And of course, 1 mole is x, for 1 mole x moles dissociated, for 1 mole of H2, that is also x. So, moles formed at equilibrium, moles formed are moles at total moles at equilibrium, equilibrium is equal to moles of products plus moles of reactants, but here the moles of products x plus x, and no need to write the 1 minus x because there is 1 mole, for 1 mole x moles dissociated, there is a negligible amount of moles, so we can discard that moles. So, no need to no need to add the reactant moles because x moles already dissociated. Make it remaining moles are very small in value, so we can neglect that value. So, that total moles is 2x. Right. So, mole fraction of ammonia is equal to moles of ammonia at equilibrium, that is x, moles of ammonia at equilibrium x, by total moles is 2x into total pressure is 20. Okay, x get cancelled, 20 by 2, that is 10 atmosphere. Right. And partial pressure of H2, is equal to mole fraction of H2 into total pressure. Mole fraction of H2 is moles of H2 at equilibrium by total moles. So, moles of H2 at equilibrium is x moles and total moles at equilibrium is 2x and total pressure is 20. X's get cancelled and this also comes out to be 10 atmosphere. So, Kp is equal to partial pressure of ammonia and partial pressure of H2 gas. So, partial pressure of NH3 is 10 into partial pressure of H3 is 10 tens 100 atmosphere square. Okay, so Kp is 100 into atmosphere square. Okay. Okay. Problem 4 is a sample of pure PCl5 was introduced into evacuated vessel at 473 Kelvin. After equilibrium was attained, concentration of PCl5 was found to be 0.5 into 10 to the power of minus 1 moles per liter, and if the value of Kc, equilibrium constant Kc is 8.3 into 10 power minus 3, then what is the concentration of PCl3 at equilibrium? Already I told you equilibrium constant enables us to calculate the equilibrium concentrations of reactants or products. Okay, so when PCl5 was introduced into evacuated vessel, there established a equilibrium, that is PCl5 gives rise to PCl3 plus Cl2, right? They asked to calculate the equilibrium concentration of PCl3, and they gave that equilibrium constant Kc. Kc means equilibrium constant expressed in molar concentrations, that is Kc is equal to concentration of PCl3 by into concentration of Cl2 by concentration of PCl5. Okay. So what they gave that they gave that concentration of after equilibrium was established, after the equilibrium was attained, concentration of PCl5 was found to be 0.5 into 10 to the power of minus 1 moles per liter. That is at equilibrium the concentration of PCl5 is found to be 0.5 into 10 power minus 1, that is 0.05, that is 0.05, right? So 0.05. Okay, so at equilibrium. So at equilibrium, after the during the establishment of equilibrium, 0.05 minus x moles dissociated, that is x moles dissociated, and that x moles are dissociated, and how many moles of PCl3 formed? You can simple technique, that is take the what is it called, stoichiometric coefficients of PCl5 1 and PCl3 is 1, Cl2 1, for 1 mole x moles dissociated. So 1 mole of PCl3, how many moles? X moles, x into 1 by 1, that is x moles, and this Cl2 is x moles. Okay, so I can get the PCl3 concentration of PCl3 to concentration of Cl2 by concentration of PCl5, and if the value of Kc is 8.3 into 10 power minus 3, 8.3 into 10 power minus 3. So Kc value is 8.3 into 10 power minus 3, and concentration of PCl3 is according to our hypothecation, that is x into x by concentration of PCl5 at equilibrium 0.05, so that is 0.05, right? So 8.3 into 10 power minus 3 is equal to x square by 0.05. So x square, the next step, x square is equal to 8.3 into 10 power minus 3 into this can be written as 0.05. So 8.3 into 10 power minus 3 into this can be written as 5 into 10 power minus 2. Okay, which comes out to be this multiplication, which comes out to be 41.5 into 10 power minus 5. 41.5 into 10 power minus 5, and we can write it as 4.15 5 into 10 power minus 4. So, x square is equal to that and x is equal to, apply the root, it is approximately 2 into 10 power minus 2. So, x is the concentration of PCl3. So, PCl3 concentration is 2 into 10 power minus 2 moles per liter, right. Okay. Problem 5 is 5.1 grams of NH4HS is introduced in 3 liters evacuated flask at 327 degrees centigrade. 30% of the solid NH4SS decomposed to NH3 and H2S gases. The Kp of the reaction at 327 degrees centigrade is, right. So, R is equal to 0.08 into 0.82 atmosphere mole mass Kelvin inverse. Molecular weight of sulfur is 32 and molecular weight of nitrogen is 14. Okay. So, they asked to what they asked to calculate? They asked to calculate the value Kp. They asked to calculate the value of Kp, but they gave the data for molar concentrations. How can I know that that is the molar concentration? Because they gave that 5.1 grams of NH4HS. Okay. So, when NH4HS is evacuated in 3 liters flask at 327 degrees centigrade, equilibrium is established between NH4SH. Equilibrium is established. This is solid substance and equilibrium exists between that forms decomposed to NH3 and H2S gases, NH3 gas and H2S gas. Okay, that is also a gas. Okay, so they asked to calculate NH3 gas, NH3 gas. Okay, no need to erase this, but NH3 gas and H2S gas, right. NH3 gas and H2S gas. They asked to calculate the Kp. They asked to calculate the Kp, means that is equilibrium constant expressed in partial pressures, but we cannot get the partial pressures. So, they give that initial weight of NH4HS. So, and they gave that what is it called R value and molecular weight of sulfur and molecular weight of nitrogen. So, we can calculate the number of initial moles of NH4SS, okay, because they gave that initial moles. How can we get the initial moles? There is a they gave that weight of NH4HS 5.1 grams. And what is the molecular weight of NH4SS? They gave the molecular weight of sulfur 32 and molecular weight of 14, that is 46 plus 4 50, 50 plus 1 51. So, molecular weight is 51. So, 5.1 by 51, that is 0.1, that is 0.1. Okay, so 0.1 moles. Okay, at T equal to 0, that is these concentrations are 0. At equilibrium, during the establishment of equilibrium, okay, so equilibrium we should this is the 0.1 moles, this is the moles, 0.1 moles. Okay, but we need to Naresh we need to calculate 0.1, this is the moles, but we need to if we get the okay. So, initial moles is 0.1 moles, but they gave that 30% of solid NH4SS decomposed, only 30%. So, percentage of dissociation is 30%. So, at equilibrium that is percentage of dissociation is 0.1, 30%, 30 by 100, 0 cancel, 0.3 and it is 0.03. So, moles dissociated at equilibrium is 0.03. So, at equilibrium at equilibrium 0.11 minus 0.03 moles dissociated, 0.03 moles dissociated. So, 0.03 moles of ammonia is formed and 0.03 moles of H2S is formed. Okay. So, they asked to calculate the Kp, you should remember that point, they asked to calculate the Kp, but these are the molar concentrations. So, let us calculate the Kc value, then we go for Kp value. So, Kc is equal to concentration of NH3 into concentration of H2S by concentration of NH4S solid. Okay. So, concentration of ammonia, we know that concentration moles of ammonia at equilibrium, how can we get the concentration of ammonia from moles? Moles divided by, okay, they gave that that is a 3 liters flask, that is a 3 liters flask. So, moles divided by volume, that gives a molar concentration. So, in this much moles are presented in 3 liters. So, concentration of NH3 is equal to moles 0.03 by 3 liters, that is 0.01 molar concentration, and concentration of H2S is 0.03 moles formed by volume, that is 3 liters, that is which also comes out to be 0.01. So, concentrations of NH3 and H2S are 0.1. But what is the concentration of NH4SH? NH4SH is a solid. We usually we take the solid concentration as unit. So, 1 unit. So, Kc is equal to, concentration of NH3, that is 0.01 into concentration of H2S 0.01. This is 10 power minus 2 and this is 10 power minus 2, that is 10 power minus 4 moles square plus liter square, moles square by liter square, right. So, Kc. So, but they asked to calculate the Kp value. So, the Kp of the reaction at 327 degrees centigrade, and they gave that R value also. We know the relation between Kp and Kc. Kp is equal to Kc into RT power delta n. So, Kp is equal to Kc in how much we get 10 power minus 4. R value, R is 0.082. So, there is simple technique 0.082, this can be written as 1 by 12. So, 1 by 12 that gives 0.0823, the almost 1 by 12 is equal to 0.082. That is why instead of R we can write 1 by 12. Okay. So, 1 by 12. Okay. And temperature should be in Kelvin scale. So, temperature is 327 degrees centigrade. You have to add the 273 to convert the degree centigrade temperature into kelvins, that is 600. So, that is 600. Delta n is already I told you in the earlier classes. Delta n is a number of gaseous products minus number of gaseous reactants. Number of moles of gaseous products is this is 1 mole and this is 1 mole. So, gaseous products moles is 2, and number of moles of gaseous reactants, there is no gaseous reactant. So, here this there is a solid. So, delta n which comes out to be 2, because number of gaseous products here the NH3 and H2S are gases. So, number of moles of gaseous products is 2, and number of moles of gaseous reactants, there is no gas in the reactant, there is a solid in the reactant. So, no need to take into consideration, right. So, 10 power minus 4 into 1 by 12 into 600 whole square, okay, 10 power minus 4 which comes out to be this is 5, 12, 60, this 50, that is 50 square. So 10 power minus 4, this is 50 square 2500, 10 power minus 4 into 2500. Okay, this 10 power minus 4, that is 0.2500. So Kp is 0.2500. Okay, so in this way we can calculate the Kp from Kc value. So what that you should remember is you should read the given data. What the given data, you should understand the problem. So first of all you should understand the problem, what they provided and what they asked to calculate. Okay, they asked to calculate Kp, but they provide the data for molar concentrations. So you should remember, you should understand the problem properly, then only you can solve the problem. I hope these problems will help you to solve the more complicated problems. Okay, I hope you all understand these problems, and thank you for watching.